Hey everybody, brand new topic in this video on momentum. So let me just start with the definition. So the definition of momentum is, say you have a mass traveling with some velocity. So some mass, some velocity. Momentum is a vector, p, which is just the product of the mass and the velocity. That's it. And the units are kilogram, meters per second. There's no special unit that we named after somebody. Okay, so that's it. And next definition, impulse. So let's say there's a wall over here. So this mass is flying toward the wall, hits the wall. Let's say it's a ball or something. It deforms a little bit and then bounces off the wall, goes this way. Let's say you put a sensor right here on the wall and you measure the force as a function of time. Okay, then when the mass is traveling toward the wall, right, it's not touching the wall yet, and then as it starts to make contact, right, it starts to deform a little bit, the force goes up, and then it's like going back to its original shape and then goes flying off. So let's say the force you measure with that sensor looks like this. The impulse is a vector, we'll call it J, which is this integral. So this is some function, right? This is some function, f of t. You integrate that over time. From, we have to decide on some initial point and final. So let's say I'll call this t initial. I'm going to call over here t final. You integrate from there to there, right? So it's this area under the curve. That's impulse. Okay, so we got these two brand new definitions. And we can make an approximation. So let's say we model this kind of bell-shaped curve with a rectangle, say like this. So the same time interval from t initial to t final, but some different average force where this area is the same as this area. So same area. By same area, I mean the same impulse, but it's an approximation. So instead of this kind of function, this is just a constant. So the approximation is some average force, which is a constant, as opposed to a function, times this time interval from initial to final. So delta t. Okay. So this was already a lot of information. Let's talk about impulse a little bit with an example. Let's say you have some model rockets. So the model rocket motors have classifications. So let's say you go to the store and you buy some, I'll just have a few. You buy a few rocket motors. Okay, it's classified like this. The letter is the impulse. So let's say this one is 5 Newton seconds. And C is double, 10 Newton seconds. So this is also 5. And then the number next to the letter is that average force, the thrust. So something like this maybe looks like this, but you approximate it like a rectangle where this average force is 5. Which means, what would the time interval be? Right? If the average force is 5 newtons and the impulse is 5 newton seconds, then this time interval has got to be 1 second. Right? And then let's say you have your B10 rocket motor. So if the B5 looks like, let's say like this, where this is 5 newtons and 1 second, the B10 looks like 10 newtons, and then how many seconds? Has to be half a second. Right? Because this impulse is 5, right? Because it's a class B motor. They're both 5. Right? This has the same area as this. But then it's a matter of, do you want more thrust for less time or less thrust for more time? And then let's say you go to C5. So it's still 5 newtons of thrust like this, but then the impulse is 10 newton seconds. So that means it's got to be going for 2 seconds. 5 newtons for 2 seconds, 10 newton seconds. Compared to something like this, that's 10 newtons of thrust, but then the impulse is 10, so it's got to be 10 newtons for 1 second is 10 newton seconds. Okay, so that's how impulse works, and then all of these curves are approximations, right? The curves actually look like this. So let's see, let's just make up another, let's say D 10. What is that going to look like? So D is double here, so 20. So then that would be 10 newtons of thrust for how long? 10 newtons of thrust for 2 seconds. 10 times 2 is 20. Right, or let's make up another one. How about E 4? So E is going to be double of D, so that's going to be 40. So E4 means 4 newtons, and then it's going to have to be going for 10 seconds like this, right? 4 newtons for 10 seconds is 40 newton seconds. Or if you have like E20, then that's going to be like 20 newtons of thrust for 2 seconds. So like this. And the curve, looks like this. Okay, so I hope you have a feel for impulse. And let's just do one more formula. Okay, so back to the definition of impulse. Let's do 2 more formulas, and then we'll stop, and then we'll switch to another video, because this is a lot of information. Okay, so for momentum, recall Newton's second law. Okay, acceleration is actually the time derivative of velocity. Now, mass is a scalar. So what if I move the scalar over here, like this? Right, you can move a scalar, and that is, by definition, momentum. Okay, so let me write that again. Sum of forces equals the time derivative of momentum. This is Newton's second law. When we first started, this was how we defined Newton's second law, because at the time we did not yet define momentum, but now you know. So here you go, Newton's second law. Okay, impulse was this. Now force is, let's go back to here, mass times acceleration. And then let's assume that mass is constant. I can take that out of the integral. Okay, what's the integral of acceleration with respect to time? Velocity. And then let's put the limits, right? From some initial to some final. So from like this. And then mass times velocity is momentum. So change in momentum. So impulse is the change in momentum. And this is called the impulse momentum theorem. Okay. Now, I'll just foreshadow the next video. If we tie everything together for collisions, then let's say you have one object here going this way, some initial velocity, some object here with some initial velocity, and the two objects collide like this. And then let's say they go bouncing off the other way. So this has some final velocity. Okay. While these two objects are in contact, then say mass 1, there's some normal force on mass 2. And then for mass 2, there's some normal force from mass 1. So for this system, during the collision, at this instant, if we sum all the forces, there's a force from mass 1 on mass 2, and there's a force from mass 2 on mass 1. And we know now sum of forces equals the time derivative of momentum. Now, during the collision, right, these are action-reaction. It's an action-reaction pair. So by Newton's third law, the force of 1 on 2 is equal and opposite the force of 2 on 1, which means this whole thing is 0. Okay, so then let me write this one more time. The time derivative of momentum is 0. And what does that mean? When the time derivative of something equals 0, that something is constant. Okay, so during a collision, momentum is constant, or another way to say that is conserved. Okay, so let's save this for another video and just explore collisions and this conservation of momentum. Right, this is a lot of information for one. Okay, so I'll see you on that next video.